Hello and welcome. Find a comfortable position. Allow your breathing to slow. Tonight, we are not here for high-octane adventure or dramatic revelations. We are here to learn, to wonder, and perhaps to drift away on a current of cosmic curiosity. This is Plunge into Science, an experience designed to enlighten your mind and soothe your spirit. Think of this as a late-night lecture in the grandest classroom of all, the universe itself. We're going to journey to a place of profound solitude, to meet an object that challenges our very definition of the word planet. But before we embark on our journey to the loneliest world we've ever found, I have a question for you. Take a moment. What is your favorite planet? Is it the fiery, rusted plains of Mars? The majestic, swirling storms of Jupiter with its iconic great red spot? Or perhaps the ethereal beauty of Saturn, adorned with its breathtaking rings? Each one is a character in the grand story of our solar system. Hold that image in your mind. Today, we are going to add a new character to your cosmic roster, one that lives a very different life. Prepare to meet PSO J318.5-22, the loneliest planet in the universe. To understand loneliness on a cosmic scale, we must first appreciate the scale itself. Imagine the entire universe as a vast, dark ocean. In this ocean, there are islands of light. These islands are galaxies, magnificent swirling collections of hundreds of billions of stars. Our home, the Milky Way, is one such island. Now, let's zoom into our island. Within this galaxy, the stars themselves are like tiny, glowing embers separated by distances that are almost impossible for the human mind to truly grasp. The nearest star to our sun, Proxima Centauri, is over 4 light years away. That means if you were to travel at the speed of light, the fastest anything can possibly travel, it would still take you more than 4 years to get there. Our fastest spacecraft would take tens of thousands of years to complete the same journey. This is the fundamental nature of our universe. It is overwhelmingly, profoundly empty. The space between stars, known as interstellar space, is a near-perfect vacuum, colder and emptier than anything we can create on Earth. It is in this immense, silent darkness that most of the universe exists. The planets we know and love, Earth, Jupiter, Saturn, are defined by their relationship to our star, the Sun. They are tethered to it by the invisible, unwavering force of gravity. They dance in predictable, elegant orbits, bathing in its light and warmth. This is our model for a planetary system. It feels normal, correct, like a family gathered around a hearth. The star is the parent, the provider of energy, and the planets are its children, each with its own unique personality, but all belonging to the same system. This concept of belonging is central to our astronomical perspective. We categorize celestial objects based on their relationships. A moon orbits a planet. A planet orbits a star. A star orbits the center of a galaxy. Everything seems to have its place in this grand cosmic hierarchy. But what if an object breaks from this hierarchy? What if a planet, a world that should, by our definitions, be orbiting a star, isn't? What if it's adrift in that vast, empty ocean between the stars? This is not just a theoretical question. The universe, we are learning, is filled with such wanderers. These are the rogue planets, or as they're sometimes more poetically called, orphan planets. They are worlds without a sun, cast out from the gravitational embrace of their parent star to journey through the interstellar darkness alone. For a long time, these objects were purely hypothetical. How could we possibly see a dark, cold planet in the overwhelming blackness of space without the light of a nearby star to illuminate it? It would be like trying to find a single fleck of soot in a vast, dark cave. It seemed an impossible task, but as our technology has grown more sophisticated, we have begun to pierce that veil of darkness. We're starting to find them. And in doing so, we are finding that the universe is a far stranger and perhaps more melancholic place than we ever imagined. Does an object's value or identity come from what it is connected to? Or does it possess an inherent identity all its own, regardless of its attachments? Ponder that as we prepare to meet the most famous of these cosmic castaways. Before we can truly appreciate the uniqueness of a rogue planet, we must first ask a deceptively simple question. What is a planet? For most of human history, the answer was easy. A planet was one of the wandering stars in the night sky, those points of light that moved against the backdrop of the fixed constellations. The word planet itself comes from the Greek word planets, meaning wanderer. This definition served us well for millennia. We identified Mercury, Venus, Mars, Jupiter, and Saturn. With the invention of the telescope, we added Uranus and Neptune to the family. And then, in 1930, we found Pluto. For over 70 years, our solar system had 9 planets. It was a fact taught in every classroom, a piece of fundamental knowledge. But as our ability to see deeper into space improved, this simple picture began to get complicated. In the 1990s and early 2000s, astronomers started discovering other objects in the outer solar system, in a region known as the Kuiper Belt. Objects like Eris, Makemake, and Haumea. Eris, in particular, was found to be even more massive than Pluto. This created a dilemma. If Pluto was a planet, then surely Eris had to be a planet as well. And if Eris was a planet, what about the dozens or potentially hundreds of other large, round objects we were beginning to find out there? Will we soon have a solar system with 50 planets? 100? The scientific community realized that our old, informal definition was no longer sufficient. We needed a clear, scientific classification. In 2006, the International Astronomical Union, IU, met to settle the debate. They established a 3-part definition for a planet in our solar system. First, the object must be in orbit around the sun. Second, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a nearly round shape, a state known as hydrostatic equilibrium. Third, it must have cleared the neighborhood around its orbit. This last criterion is the most controversial. It means the object must be the dominant gravitational force in its orbital zone, having either absorbed or flung away most other objects. Jupiter has certainly cleared its neighborhood. Earth has too. Pluto, however, has not. It shares its orbital space with many other objects in the Kuiper Belt. And so, with this new definition, Pluto was reclassified as a dwarf planet. This decision remains controversial to this day, but it highlights a crucial point. Our definitions are man-made tools we use to categorize a complex and messy universe. Now consider our subject, PSO J318.5-22. Let's apply the IU definition. Is it in orbit around the sun? No, it's not in our solar system at all. It drifts through interstellar space. Right there, by the very first criterion, it fails the test to be a planet in our system. But this is where the definition itself shows its limitations. The IU definition was specifically designed for our solar system, what we call a planetary mass object that doesn't orbit any star. This is the category our lonely wanderer falls into. It is massive enough to be round, estimated to be about 8 times the mass of Jupiter. It is, for all intents and purposes, a world. It just doesn't have a star to call home. This forces us to question the very foundation of our classifications. Is a planet defined by its parent star or by its own intrinsic nature? Is a planet a role it plays in a system, or is it a state of being? PSO J318.5-22 exists as a profound counterargument to our sun-centric view of the cosmos. To understand how a planet can become an orphan, we must first witness the environment of its birth. And that environment is anything but peaceful. Our solar system today is a relatively calm and orderly place. The planets move in stable, predictable orbits. But it wasn't always this way. The birth of a star system is a process of unimaginable violence and chaos. It all begins in a stellar nursery, a vast cold cloud of gas and dust known as a giant molecular cloud. These clouds can be hundreds of light years across, containing enough material to form thousands or even millions of stars like our sun. Within these clouds, a pocket of gas and dust can begin to collapse under its own gravity, perhaps triggered by the shockwave from a nearby supernova. As this material collapses, it begins to spin faster and faster, just as an ice skater spins faster when they pull their arms in. This spinning motion flattens the collapsing cloud into a disk of material around a hot, dense core. This core will eventually ignite with nuclear fusion and become a star. The disk surrounding it is called a protoplanetary disk. This is the crucible where planets are forged. Inside this swirling disk of gas, ice, and dust, tiny particles begin to stick together through electrostatic forces. They form larger and larger clumps, like dust bunnies under a bed. These clumps grow into pebbles, then boulders, then kilometer-sized objects called planetesimals. This is a brutal process. For every planetesimal that survives, thousands are shattered in high-speed collisions. The ones that do survive continue to grow, their gravity becoming stronger and stronger, allowing them to sweep up more and more material in their path. This is called accretion. Over millions of years, these planetesimals grow into planetary embryos, or protoplanets, the size of our moon or Mars. The largest of these protoplanets then begin to dominate their regions of the disk, either consuming their smaller rivals or flinging them into different orbits in a gravitational game of billiards. This early stage of a solar system is a cosmic demolition derby. Imagine dozens of Mars-sized objects careening around the young star, their orbits crossing and interacting. The gravitational forces at play are immense and unpredictable. A close encounter between two massive protoplanets can have dramatic consequences. One object might be sent spiraling into the parent star to be consumed. Two objects might collide and merge, forming an even larger planet. This is how we believe our own moon was formed, from a collision between the young Earth and a Mars-sized object named Theia. And sometimes, in a particularly powerful gravitational interaction, a planet can be accelerated to such a high speed that it achieves escape velocity. It is flung out of the system entirely, like a stone from a slingshot, destined to wander the cold, dark void between the stars forever. This is the most likely origin story for a rogue planet. It is not born alone. It is born as part of the family, only to be violently exiled in the chaotic turmoil of its youth. Does this cosmic eviction make it a refugee? Or is it simply an object following the indifferent laws of physics? Its existence is a testament to the fact that for every stable, peaceful solar system we see, there is a hidden history of chaos, collision, and loss. For decades, the existence of rogue planets was a compelling theory, but we had no direct proof. How could we possibly find a dark object against a dark background? The answer came not from looking for what we could see, but from looking for what we couldn't see in visible light. Planets, even rogue ones, are not entirely cold. Especially when they are young, they retain a tremendous amount of heat from their formation. The process of accretion and gravitational collapse generates immense energy, and this heat radiates away over billions of years. However, this heat is not emitted as visible light like a star. It is emitted as infrared radiation, which we perceive as heat. To find a rogue planet, you don't need a traditional telescope. You need an infrared telescope, a heat-seeking eye on the universe. Enter the Panoramic Survey Telescope and Rapid Response System, or PanSTARRS. Located atop the Haleakala volcano in Maui, Hawaii, PanSTARRS-1 is a survey telescope with a massive 1.8-meter primary mirror and one of the largest digital cameras in the world. Its primary mission is to scan the entire available sky several times a month, looking for moving objects like asteroids and comets that might pose a threat to Earth. But in doing so, it has created one of the most comprehensive digital maps of the sky ever produced, not just in visible light, but in near-infrared wavelengths as well. In 2013, a team of astronomers led by Dr. Michael Liu of the University of Hawaii's Institute for Astronomy was sifting through this mountain of data. They were looking for something very specific, faint, red objects that appeared to be moving. Why red? because cooler objects emit most of their energy at longer, redder wavelengths. A hot star like our sun shines with a yellowish-white light. A cooler red dwarf star shines, well red. An even cooler object like a young, warm planet would appear exceptionally red in astronomical filters, glowing faintly in the infrared spectrum. The team combed through data from pan-stars and cross-referenced it with data from another infrared survey, the WISE, Wide Field Infrared Survey Explorer satellite. They were hunting for objects that were too faint and too red to be stars, but that were clearly present in the sky. And then they found it, a faint, solitary dot of light, moving with the stars in a nearby stellar association, but shining on its own. It had no parent star. It was given the official, rather unpoetic designation, PSO J318.5-22-22.8603, which we shortened to PSO J318.5-22. The discovery was a watershed moment. It wasn't the first candidate for a rogue planet, but it was by far the clearest and most unambiguous. Previous candidates have been found through a technique called gravitational microlensing, which detects a planet by the way its gravity briefly bends the light of a distant star. But that method is fleeting and provides limited information. PSO J318.5-22 was different. We could see it directly. We could point our best telescopes at it and study its light, its heat, its color. We could analyze its spectrum to understand the chemistry of its atmosphere. For the first time, we had a rogue planet that we could study as an individual object, a world with its own properties and its own history. It was no longer just a ghost in the data. It was a real place. How does it feel to know that our technology has advanced to the point where we can find a single, sunless world adrift over 80 light years from Earth? It is a profound testament to human ingenuity and our unyielding desire to see what lies hidden in the dark. So, what is this lonely world actually like? Let's put together a profile of PSO J318.5-22 based on the data we have painstakingly gathered. It is located approximately 82 light years from Earth, which is relatively close in galactic terms, making it one of our neighbors. The most striking characteristic is its mass. It is estimated to be around 8 times the mass of Jupiter, our solar system's largest planet. This makes it a true heavyweight, firmly in the gas giant category. Like Jupiter, it has no solid surface to stand on. It is a colossal ball of gas and liquid, primarily hydrogen and helium, that grows denser and hotter the deeper you go. If you were to descend into its atmosphere, the pressure and temperature would eventually become so extreme that the hydrogen gas would compress into a liquid and then into a bizarre state known as metallic hydrogen, which is a super hot, electrically conductive fluid. At its very core, there may be a small, rocky, or icy center, a remnant of the original seed from which it grew, crushed under millions of times the atmospheric pressure of Earth. Its age is another crucial piece of the puzzle. By studying its motion through space, astronomers have determined that it belongs to a collection of young stars called the Beta Pictoris moving group. All the stars in this group were born from the same stellar nursery at roughly the same time. This makes them cosmic siblings. And by dating the other stars in the group, we can confidently say that PSO J318.5-22 is very, very young in astronomical terms, only about 12 million years old. For comparison, our solar system is 4.6 billion years old. This means that PSO J318.5-22 is still a planetary infant. This youth is the reason we can see it at all. It is still glowing with the primordial heat of its violent formation. Its effective temperature is estimated to be around 1,100 Kelvin, or about 800 degrees Celsius, 1,500 degrees Fahrenheit. While incredibly hot by human standards, this is exceptionally cold for a celestial object that shines on its own. The dim, faint light it emits would be a deep, dull, magenta color to our eyes, a ghostly glow in the interstellar night. Because it doesn't orbit a star, it has no year, A year is defined by the time it takes a planet to complete one orbit. With no orbit to complete, the concept is meaningless. It also has no day in the traditional sense of a star rising and setting. It likely rotates on its axis, perhaps very quickly like Jupiter, creating a cycle of sorts, but without an external light source, there is no dawn or dusk. The sky, from within its upper atmosphere, would be eternally black, punctuated only by the distant cold light of the stars of the Milky Way. There are no seasons driven by axial tilt, no variation in the energy it receives. The only energy source is the relentless, slow leakage of its own internal heat. It is a world of profound constancy, a world of eternal, dimly lit twilight. When we think of a planet, we instinctively think of its relationship with the sun. We think of sunrises, seasons, years. PSO J318.5-22 forces us to discard all of that. It exists for itself, governed only by its own internal physics. Is a world defined by its cycles and changes, or can a place of eternal, unchanging twilight still be considered a dynamic world? Seeing a faint dot of light is one thing. Understanding what that light is telling us is another entirely. This is the science of spectroscopy, one of the most powerful tools in an astronomer's arsenal. Every element and molecule absorbs and emits light at very specific, unique wavelengths, creating a sort of chemical fingerprint. When the faint infrared light from PSO J318.5-22 reaches our telescopes, we can pass it through an instrument called a spectrograph, which acts like a very sophisticated prism. It splits the light into its constituent colors, or wavelengths, creating a spectrum. By analyzing this spectrum, we can see which wavelengths of light are missing. These missing slivers, which appear as dark lines called absorption lines, tell us exactly what chemicals are present in the planet's atmosphere, as those are the chemicals that have absorbed that specific light. The spectrum of PSO J318.5-22 was a revelation. It looked remarkably similar to the spectra of other young, low-mass objects we had observed before, but with one key difference. It was even lower in mass. The fingerprints of water vapor and methane were present, which we expect to find in the atmospheres of gas giants. But what was truly fascinating was what the overall shape of the spectrum told us about its clouds. Unlike the ammonia and water ice clouds of Jupiter, the atmosphere of PSO J318.5-22 is so hot that its clouds are made of things we think of as solid on Earth. The data suggests the presence of thick, roiling cloud decks made of molten silicates, essentially liquid rock and dust, and even droplets of molten iron. Imagine a sky not with fluffy white clouds of water, but with dark, glowing clouds of lava and liquid metal, swirling in massive, planet-girdling storm systems. These clouds are not static. By observing the planet over time, astronomers have noticed that its brightness varies significantly and rapidly. This suggests a highly dynamic and turbulent atmosphere. The planet is covered in massive storms, far larger than any hurricane on Earth. These storms churn up different layers of the atmosphere, bringing hotter material from deeper down to the cloud tops and revealing thinner patches in the cloud deck. This causes the amount of heat escaping into space to change, which is what we observe as a change in brightness. It is a world of perpetual, violent weather, driven not by the heat of a star, but by the planet's own internal engine. The winds on this lonely world would be ferocious, howling across a landscape of molten iron clouds at thousands of kilometers per hour. This detailed atmospheric data is what makes PSO J318.5-22 so invaluable to science. It provides a unique laboratory. On a normal planet orbiting a star, the overwhelming light of the star makes it incredibly difficult to study the faint light reflected from the planet's atmosphere. The star's glare washes everything out. But with PSO J318.5-22, there is no glare. There is no star. We get a pure, unadulterated look at the planet itself. It is a clean template for what a young gas giant planet looks like, allowing us to test and refine our models of planetary atmospheres in a way that was never before possible. It is a paradox. This object's profound isolation is precisely what makes it so revealing. It has to speak for itself, and in doing so, it is teaching us about all the other planets that are hidden in the light of their suns. Does this not speak to a deeper truth? That sometimes, only in isolation can a true character be clearly seen, without the influence of its surroundings? We've been calling PSO J318.5-22 a planet, but is that the whole story? In astronomy, the lines between categories can often be blurry. We have planets, and we have stars. But what about the objects that fall in between? This is the realm of the brown dwarfs, often called failed stars. To understand this, we need to talk about what makes a star: nuclear fusion. In the core of a star like our Sun, the immense pressure and temperature are so great that they force hydrogen atoms to fuse together to form helium. This process releases a tremendous amount of energy, which is what makes stars shine. This is the engine that powers a star for billions of years. For this hydrogen fusion to ignite, an object needs to have a certain minimum mass, which is about 80 times the mass of Jupiter. Objects less massive than this cannot ignite sustained hydrogen fusion. However, there is another, less energetic type of fusion that can occur. Deuterium, a heavier isotope of hydrogen, often called heavy hydrogen, can fuse at lower temperatures and pressures than regular hydrogen. The threshold for deuterium fusion is believed to be around 13 times the mass of Jupiter. So, we have a new category. Objects between 13 and 80 Jupiter masses are generally classified as brown dwarfs. They are more massive than planets, but not massive enough to be true stars. They have a brief period early in their lives where they fuse deuterium, giving them an extra source of internal heat, but this fuel runs out relatively quickly. After that, they simply cool and fade over time, much like a planet does. So where does PSO J318.5-22 fit in? With an estimated mass of about 8 times that of Jupiter, it falls comfortably below that 13 Jupiter mass threshold. This is one of the strongest pieces of evidence that it is indeed a planet and not a brown dwarf. It was not massive enough to even ignite deuterium fusion. All the heat and light it emits is purely the leftover energy from its formation. This is a crucial distinction. It helps us understand its origin. Stars and brown dwarfs are thought to form from the top down through the direct gravitational collapse of a cloud of gas. Planets, on the other hand, are thought to form from the bottom up through the slow accretion of material in a disk around a star. The fact that PSO J318.5-22 has a planetary mass and belongs to a moving group of young stars, the Beta Pictoris group, strongly supports the theory that it formed like a planet in a system and was later ejected. It wasn't a failed star that formed in isolation. It was a successful planet that was exiled. This distinction, however, is a subject of ongoing scientific debate. Could some low-mass objects form on their own, like stars? Perhaps the universe has more than one way to make a world. What if an object with 10 Jupiter masses formed in isolation? Will we call it a planet or a brown dwarf? Our definitions are based on a combination of mass and formation history, but we can't always know the formation history. PSO J318.5-22 is a beautiful test case because its youth and its association with the Beta Pictoris group give us strong clues about its past. It serves as a benchmark, an anchor point in this murky water between the largest planets and the smallest stars. It challenges us to think critically about our labels. Is the process by which you are made more important than what you ultimately become? Does its violent past define its present identity? A key piece of evidence in the story of PSO J318.5-22 is that it is not truly alone in its journey through the galaxy. While it has no sun, it does appear to have a family of sorts. This is the Beta Pictoris moving group. A moving group is a loose association of stars that are all moving together through space at the same velocity and in the same direction. This is a telltale sign that they all share a common origin. They were all born from the same giant molecular cloud at roughly the same time. After their birth, the gravitational tides of the Milky Way and encounters with other clouds slowly pull the original star cluster apart. But for a time, for a few tens of millions of years, the stars still travel together like a ghostly flock, a remnant of the nursery they once shared. The Beta Pictoris moving group is named after its most famous member, the star Beta Pictoris, which is known to have a massive debris disk and at least 2 giant planets of its own. The group is composed of a few dozen young, hot stars, and they are all, as we mentioned, about 12 million years old. When astronomers measured the motion of PSO J318.5-22 across the sky, they found that its trajectory was a perfect match for the other members of this group. The odds of this being a coincidence are astronomically small. It is almost certain that PSO J318.5-22 was born in the same stellar nursery as Beta Pictoris and all the other stars in the association. This provides a powerful narrative. It means our lonely planet was not a cosmic hermit that formed by itself in the middle of nowhere. It was born into a bustling, dynamic stellar neighborhood. This connection allows us to infer so much about it. It gives us a firm age, which is crucial for understanding its temperature, brightness, and evolutionary state. It also strongly suggests its origin story. The Beta Pictoris system itself is known to be a chaotic place. The planets we see, they're on slightly unusual orbits, and the debris disk is warped, all signs of strong gravitational interactions in the system's past. It is entirely plausible, even likely, that in the early days of the Beta Pictoris system, or another system within the moving group, there were more planets than we see today. In the complex gravitational dance of these young giants, one of them, our PSO J318.5-22, drew the short straw. A close encounter with a larger sibling could have given it the gravitational kick it needed to be flung out of its home system and into the interstellar void. So, while it wanders without a sun, it is still, in a way, traveling with its siblings. They are separated by light years of empty space, unaware of each other's existence, but they are all following the same path through the Milky Way. It's a poignant, almost tragic image. A family scattered across the cosmos, forever bound by a shared past, but destined to travel in solitude. Does a shared origin and a shared path constitute a connection, even if the individuals never interact again? It makes us reconsider what it means to be part of a group. Perhaps community is not just about proximity, but about a shared history and a shared destiny, even one played out across the vast, silent stage of interstellar space. The discovery of PSO J318.5-22 was a landmark, but it naturally leads to a bigger question. Is it a rare freak of nature, or is it just the tip of a cosmic iceberg? The answer, according to current scientific models and preliminary observations, is staggering. Rogue planets may not only be common, they may be one of the most numerous classes of objects in the entire galaxy. Some studies suggest that there could be twice as many free-floating Jupiter-mass planets as there are stars in the Milky Way. And when you consider smaller, Earth-mass rogue planets, the numbers could be even higher, perhaps hundreds of thousands of them for every single star. This would mean that our galaxy contains not just billions, but potentially trillions of these orphan worlds silently drifting through the darkness. Why would there be so many? It goes back to the chaotic process of planet formation we discussed earlier. The formation of a stable solar system is an inefficient and messy business. For every planet that ends up in a stable orbit, several others might be ejected. Computer simulations of planetary formation consistently show that gravitational scattering is a common outcome. The early solar system is a game of survival of the fittest, and there are far more losers than winners. The winners get a stable home around a star. The losers are cast out into the galaxy. If these models are correct, then the space between the stars is not as empty as we once thought. It is populated by a vast, unseen river of lost worlds. Detecting them is the primary challenge. Microlensing surveys have provided the most compelling statistical evidence for this large population. Gravitational microlensing occurs when a massive object, like a rogue planet, passes almost directly in front of a distant star from our point of view. The rogue planet's gravity acts like a lens, bending and magnifying the light of the background star. This causes the star to brighten for a short period, from a few hours to a few days, in a very characteristic way. By monitoring millions of stars and looking for these brief brightening events, astronomers can statistically estimate how many massive, unseen objects are drifting between us and the stars. These surveys have found numerous events consistent with rogue planets, supporting the idea of a vast, hidden population. The upcoming Nancy Grace Roman Space Telescope, with its wide field of view and incredible sensitivity, is expected to revolutionize this field. It will conduct a massive microlensing survey that could discover thousands of rogue planets, giving us our first true census of this unseen population. This opens up a new perspective on our galaxy. We tend to think of the galaxy as islands of light, stars and their systems, in an ocean of emptiness. But perhaps it's more accurate to think of it as a place teeming with dark, solitary objects, where the stars are just the lighthouses that occasionally illuminate the wanderers passing by. What does it mean for our understanding of the universe if the most common type of planet is one that has no sun? It suggests that our own solar system, with its stable, sun-drenched worlds, might be the exception rather than the rule. It paints a picture of a galaxy that is fundamentally colder, darker, and more solitary than the one we see in our night sky. When we search for life elsewhere in the universe, we typically look for planets in the habitable zone around a star, the region where temperatures are just right for liquid water to exist on a planet's surface. This is often called the Goldilocks zone, not too hot, not too cold. This model is entirely dependent on the energy from a parent star. But a rogue planet, by definition, has no parent star. It receives virtually no external heat. So, does this mean that life on such a world is impossible? Perhaps not. Our search for life might be limited by a profound lack of imagination. The key is to think beyond the surface. While the surface of a rogue planet would be frozen solid at a temperature just a few degrees above absolute zero, the interior could be a very different story. A sufficiently massive planet, especially a rocky one several times the mass of Earth, could have a hot, molten core. This internal heat comes from two sources: the leftover heat from its formation and the decay of radioactive elements in its core and mantle, the same processes that keep the Earth's core hot. This internal heat could be enough to maintain a liquid water ocean deep beneath a thick, insulating crust of ice. We have examples of this in our own solar system. Moons like Jupiter's Europa and Saturn's Enceladus are believed to have vast liquid water oceans under their icy shells, kept liquid by the tidal forces from their parent planets. A large rogue planet could achieve the same effect using only its own primordial and radioactive heat. In this deep, dark, sunless ocean, life could potentially arise around hydrothermal vents on the ocean floor. These vents, like the black smokers found in the deepest parts of Earth's oceans, spew out superheated, mineral-rich water from the planet's interior. On Earth, these vents support entire ecosystems that are completely independent of sunlight. The base of the food chain is not photosynthesis, but chemosynthesis. Microbes derive energy from chemical reactions with the minerals gushing from the vents, and larger, more complex organisms then feed on these microbes. An entire biosphere could exist in total darkness, powered by the planet's own geothermal energy. Life on such a world would be utterly alien to us. It would have no concept of day or night, of sun or sky. Its entire reality would be the crushing pressure, the chemical-rich water, and the faint warmth of the vents. Of course, this is all highly speculative. There are many challenges. Without a magnetic field generated by a rotating liquid core, a rogue planet's atmosphere could be stripped away by cosmic rays over billions of years. The energy available from chemosynthesis is also far less than that available from a star, which might limit the complexity of any life that could evolve. But the mere possibility is tantalizing. It forces us to broaden our definition of a habitable world. A habitable zone might not just be a distance from a star, but a property of the planet itself. It suggests that life might be hiding in the most unexpected of places, not just on sun-drenched surfaces, but in the dark, warm hearts of wandering worlds. Could the galaxy be filled with these hidden biospheres, each evolving in total isolation? It is a humbling thought that the greatest discoveries may lie not in the light, but in the deepest, darkest corners of the cosmos. What does the future hold for a world like PSO J318.5-22? Its journey is one of almost unimaginable timescales and distances. For millions and then billions of years, it will continue its silent voyage through the interstellar medium. Its path is governed by the overall gravitational field of the Milky Way galaxy, causing it to orbit the galactic center just as stars do, but on a solitary, independent trajectory. A full orbit around the galaxy takes hundreds of millions of years. Over these vast eons, our lonely planet will witness the birth and death of stars from afar, pass through the ghostly remnants of ancient supernovae, and drift through vast, colorful nebulae where new generations of stars and planets are being born. It will be a silent observer of the galaxy's grand, unfolding drama. As it travels, it will be slowly, inexorably cooling. The primordial heat from its formation is a finite resource. Over billions of years, this heat will radiate away into the cold of space. Its faint magenta glow will fade, shifting to a deeper red and then disappearing from the infrared spectrum altogether. Eventually, it will become a truly dark object, a cold, inert ball of gas, its temperature settling to just a few degrees above absolute zero, the background temperature of the universe. It will become a true ghost, detectable only by its gravitational influence on anything it might pass. What are the possible fates that could interrupt this long, slow fade into darkness? There are a few intriguing possibilities. One is capture. If the rogue planet passes close enough to another star system, it could be gravitationally captured, becoming a new, distant planet in that system. This is a low probability event, as space is so vast, but over billions of years, the odds increase. If captured, it would be a strange newcomer, a planet with a different age and composition from its new siblings. Its orbit would likely be highly elliptical and inclined, a testament to its dramatic past. It would once again have a sun, but it would be a foreign one. Another possibility is a close encounter that doesn't result in capture, but does alter its path, sending it careening off in a new direction. An even more dramatic fate would be to be flung out of the galaxy altogether. A close pass by a massive star or a star cluster could accelerate it to galactic escape velocity, ejecting it from a Milky Way into the even greater emptiness of intergalactic space. There, it would wander in an ocean of true nothingness, with only the faint, fuzzy light of distant galaxies to mark its passage. The most final end, on a timescale so long it is almost meaningless, would be to be consumed by a black hole. But most likely, its fate is simply to drift, to cool, and to fade, a quiet testament to a brief, fiery youth, followed by a long and silent adulthood. Is a journey without a destination still a meaningful one? For PSO J318.5-22, the journey is all there is. Let us take a moment to pause our scientific inquiry and reflect on the emotional and philosophical weight of what we are discussing. We call PSO J318.5-22 the loneliest planet. But can a planet, a non-sentient ball of gas and rock, truly be lonely? Loneliness is a complex human emotion, born from a consciousness that desires connection. To project this feeling onto a celestial object is a form of anthropomorphism. It is us seeing our own capacity for solitude and isolation reflected in the cosmos. And yet, the label feels appropriate, doesn't it? It speaks to a deep, intuitive understanding of its condition. It is separated, disconnected, adrift from the type of system that we consider to be a cosmic home. This act of naming and describing reveals more about us than it does about the planet. Our quest to understand the universe is also a quest to understand ourselves. When we look at Earth, we see a vibrant, interconnected world teeming with life. We call it home. When we look at Mars, we see a desolate, quiet world, and we feel a sense of loss for what it might have been. When we look at PSO J318.5-22, we see a world in ultimate isolation, and we call it lonely. Each of these perceptions is a mirror. The universe is a canvas, and we paint our own hopes, fears, and emotions onto it. Consider the concept of perspective. From our vantage point on Earth, nestled in our comfortable solar system, the rogue planet's existence seems tragic, a story of exile and solitude. But from what perspective would the planet itself view its existence if it could? It knows no other reality. It has no memory of sun's warmth to miss. Its entire existence is the eternal, dark twilight, the internal heat, the swirling storms of its own atmosphere. To it, this state of being would simply be normal. Perhaps our sun-centric view is a form of bias. We see the star as the center, the most important part of the system. But to a world powered by its own internal engine, a star might be an irrelevance, or even a violent, disruptive force. This lonely planet forces us to confront the vastness of cosmic experience. It reminds us that our way of being, tethered to a star, bathed in light, with cycles of day and night, is just one of many possibilities. The universe does not owe us familiarity. It is under no obligation to conform to our expectations of what a home or a family should look like. There are worlds of eternal day, locked to their stars. There are worlds of eternal night, like this one. There are worlds that dance with multiple suns. Each has its own reality. PSO J318.5-22, in its profound solitude, does not ask for our pity. Instead, it offers us a profound gift, the gift of perspective. It challenges us to decenter ourselves from our cosmic story and to appreciate the sheer, unbiased diversity of existence. Does an existence need to be witnessed by another to have meaning? Or is the simple act of being, of persisting through eons in the silent dark, a meaning all its own? The story of planetary ejection is not just something that happens in distant, exotic systems like the one that gave birth to PSO J318.5-22. It is very likely part of our own solar system's history. The calm, clockwork precision of our current planetary orbits hides a violent and tumultuous past. Modern models of our solar system's formation, like the Nice model, named for the city in France where it was first developed, suggest that our giant planets, Jupiter, Saturn, Uranus, and Neptune, formed much closer to the Sun and to each other than they are today. Their early orbits were not stable. According to this model, the early solar system was a crowded place. The giant planets migrated, their powerful gravitational fields interacting and resonating with each other. At some point, this dance became unstable. Jupiter and Saturn entered a powerful orbital resonance, which destabilized the entire outer solar system. This gravitational chaos sent Uranus and Neptune spiraling outwards to their current positions. In the process, their immense gravity would have acted like a cosmic broom, sweeping through a primordial disk of countless smaller icy bodies, planetesimals, sending them scattering in all directions. This event is thought to be the cause of the late heavy bombardment, a period about 4 billion years ago when the inner planets, including Earth and the Moon, were pummeled by asteroids and comets. But it wasn't just small bodies that would have been scattered. It is almost certain that in the midst of this chaos, entire planets were ejected from our solar system. Some simulations suggest that the early solar system may have had 1 or 2 additional ice giant planets, similar to Uranus or Neptune, that were tossed out into interstellar space during this migration. If this is true, it means that somewhere out there, drifting through the Milky Way, are the lost siblings of Earth, Mars, and Jupiter. They are rogue planets, born from the same cloud of gas and dust as our own world, now wandering the galaxy as cosmic orphans. We will likely never find them. They are too far away, too cold, too dark, but their ghosts haunt the models of our own history. This idea even touches on one of the great modern mysteries of our solar system, the hunt for Planet 9. The strange, clustered orbits of several distant objects in the Kuiper Belt suggest the gravitational influence of a large, unseen planet far beyond Neptune. One hypothesis for the origin of this potential Planet 9 is that it could be a captured rogue planet, a wanderer from another star system that strayed too close to our own sun and was drawn into a vast, distant orbit. So, not only might we have lost planets, we might have gained one as well. Our solar system family may not be entirely of one blood. It is a humbling thought. Our neat, tidy family portrait of 8 planets might be missing members who were exiled and might include an adopted child from a distant star. It reminds us that no system is an island. The galaxy is a dynamic place, and its history is one of constant interaction, loss, and sometimes unexpected additions. Finding PSO J318.5-22 was a triumph of modern astronomy, but it was like finding a single remarkable shell on an unexplored beach. We know the beach is vast and likely covered in shells, but we have only just begun to look. The next generation of telescopes, both on the ground and in space, are poised to turn our speculative census of rogue planets into a hard catalog of discoveries. The future of this science is incredibly bright, even if its subjects are dark. The most anticipated instrument in the hunt for rogue planets is NASA's Nancy Grace Roman Space Telescope, slated for launch in the mid-2020s. Roman is designed for large-scale cosmic surveys. Its key feature is a wide-field instrument that can capture an area of the sky 100 times larger than the Hubble Space Telescope in a single snapshot, but with the same exquisite resolution. One of its primary missions will be to conduct a massive gravitational microlensing survey towards the dense star fields at the center of our Milky Way. As we discussed, microlensing is the most powerful technique for detecting these dark worlds statistically. Roman will monitor hundreds of millions of stars continuously, and it is expected to detect thousands of lensing events caused by rogue planets, from massive gas giants down to worlds smaller than Mars. This will give us our first real understanding of their population statistics. How many are there? What is the most common size? Are smaller, rocky rogue planets more common than large, gassy ones? Roman will answer these fundamental questions. In addition to microlensing, the direct imaging of rogue planets will also take a giant leap forward. On the ground, massive new observatories like the extremely large telescope, YELT, and the Giant Magellan Telescope, GMT, are under construction. With primary mirrors tens of meters in diameter, they will have unprecedented light-gathering power and resolution. They will be equipped with advanced adaptive optic systems, which use lasers and deformable mirrors to cancel out the blurring effect of Earth's atmosphere, providing images as sharp as those from space telescopes. These giants will be able to directly spot young, warm rogue planets like PSO J318.5-22 at even greater distances, and they will be able to perform much more detailed spectroscopic analysis of their atmospheres. And of course, there is the James Webb Space Telescope, JWST. As our premier infrared observatory in space, JWST is perfectly suited to studying these dim, cool objects. While it's not a survey telescope designed to find new ones, it is the ultimate tool for characterizing the ones we know about. Scientists are already using JWST to get incredibly detailed spectra of known brown dwarfs and a few rogue planet candidates, probing their atmospheric chemistry for signs of different types of clouds, weather patterns, and molecular compositions in ways we could only dream of a decade ago. Each new instrument, each technological leap, peels back another layer of the darkness. We are moving from an era of a single, remarkable discovery to an era of big data and statistical science. We are preparing to map the unseen, to chart the great dark river of wandering worlds that flows through our galaxy. Close your eyes for a moment. Let the visuals fade and just listen. What would a world like PSO J318.5-22 sound like? On Earth, Our soundscape is dominated by life and by weather driven by the sun. We hear the rustle of leaves in the wind, the crash of ocean waves, the chirping of birds, the hum of insects. All of this is powered directly or indirectly by sunlight. On a rogue planet, there is none of that. There is no life as we know it to make noise. There are no oceans of water to crash upon a shore. The silence would be of a kind we can barely comprehend, but it would not be a complete and total silence. There would be sound, born from the planet's own internal energy and geology. Let's imagine we have a probe descending through its atmosphere. As we enter the upper layers, we would hear the hiss of thin gas, a whisper of hydrogen and helium rushing past. Deeper down, we would encounter the ferocious winds. These would not sound like winds on Earth. In an atmosphere far denser than our own, the wind would be a physical presence, a deep, resonant bass roar that would vibrate through the very structure of our probe. It would be the sound of immense energy, of continent-sized storms churning the molten clouds. And what are those clouds? The clouds of liquid iron and silicate dust. We might hear the percussive sound of metallic rain, not the gentle pitter-patter of water, but a heavier, sharper sound, like hot sand being thrown against a metal sheet. Perhaps there would be lightning. On Jupiter, we see massive lightning flashes hundreds of times more powerful than any on Earth. On a world with clouds of molten iron, the electrical discharges could be on an even grander scale. We would hear the deafening, explosive crack of lightning bolts that stretch for thousands of kilometers, their thunder a rolling, gut-shaking boom that would echo for hours through the dense atmosphere. Deeper still, as the pressure mounts and the gas turns to liquid, the sounds would change. We would hear the groans and creaks of the planet itself, the seismic rumbles of its interior, the deep, planetary hum of its cooling core. It would be a soundscape of immense power and profound desolation. A symphony of physics, not biology. It would be the sound of a world talking to itself in the dark. This exercise in imagination is important because it reminds us that these are not just data points or abstract concepts. They are real places. They have atmospheres. They have weather. They have a physical reality. PSO J318.5-22 is not just a lonely object. It is a world with its own character, its own voice. And even if we're the only ones to ever hear it, its song of solitude plays on, an eternal, deep note in the grand silence of interstellar space. Can a sound that is never heard truly be said to exist? It's a classic philosophical riddle, but in the context of the cosmos, it takes on a new, more profound meaning. In science, we often learn the most from the exceptions, from the outliers that don't fit neatly into our models. PSO J318.5-22 is one such object. Its existence as a free-floating, directly imaged planet of known age and mass makes it an invaluable scientific anchor, a benchmark against which we can measure and understand other, more complex systems. Its primary value lies in its isolation. When we study a planet that orbits a star, especially a gas giant orbiting very close to its star, a hot Jupiter, we face a fundamental problem: the star. The star is 1 billion times brighter than the planet. Teasing out the faint light of the planet from the overwhelming glare of its sun is one of the most difficult technical challenges in modern astronomy. We have to use complex techniques like coronagraphs to block the starlight and sophisticated algorithms to subtract its glare. Even then, the data we get from the planet is often noisy and contaminated. PSO J318.5-22 has no such problem. It provides a pure, clean signal. The light we receive from it is all from the planet. This allows us to create exceptionally clear models of what a young gas giant's atmosphere looks like and how it behaves. We can study its chemical composition, its cloud structure, its temperature profile, and its weather patterns without any stellar contamination. This pure planet then becomes our template. When we later study a hot Jupiter orbiting a star, we can use our models from PSO J318.5-22 as a guide. If the hot Jupiter spectrum looks different, we can ask why. Is it because of the intense radiation from the star? Is the star's heat changing the cloud chemistry? Is the star's gravity causing tidal effects? By comparing the complex case, the orbiting planet, to the simple, clean case, the rogue planet, we can begin to untangle the different physical processes at play. It is a Rosetta Stone for exoplanet atmospheres. Just as the Rosetta Stone allowed us to decipher Egyptian hieroglyphs by providing a known Greek text alongside them, PSO J318.5-22 allows us to better decipher the complex signals from star-hugging planets by providing a clean, known baseline. For example, by studying the colors and brightness variations of this lonely world, we have learned immense amounts about the properties of iron and silicate clouds in planetary atmospheres. This knowledge is now being directly applied to our interpretation of data from planets orbiting other stars, including those observed by the James Webb Space Telescope. So, ironically, the loneliest planet in the universe is helping us to better understand its more sociable cousins throughout the galaxy. It is a reminder that in science, as in life, sometimes the best way to understand a complex relationship is to first study the individuals in isolation. Its solitude is not a scientific hindrance. It is its greatest asset. It is a quiet teacher offering up its secrets to anyone with a telescope powerful enough to listen. What other secrets are hidden in objects we have dismissed as oddities? It shows that sometimes the most profound discoveries come from looking where everything else isn't. The concept of home is central to the human experience. For us, it is this blue marble, our Earth, in a stable orbit around a yellow star. This is our baseline, our definition of normal. But the universe is constantly challenging this definition. The discovery of PSO J318.5-22 and the realization that trillions of such worlds may exist forces a fundamental reevaluation of what a planetary home can be. Our model of a sun and its orbiting family is just one of many possible arrangements. It may not even be the most common one. Imagine a civilization, if one could exist in such a place, that evolved in the deep, dark ocean of a rogue planet. Their concept of home would be the geothermal vent that provides them with warmth and sustenance. The universe, to them, would not be a sky of brilliant lights, but an eternal, pressurized darkness. The idea of a sun, a giant ball of fire in the sky, would be a myth, a wild fantasy. Their entire physics, biology, and philosophy would be shaped by an existence powered from within. Who are we to say that our sun-drenched existence is more of a home than theirs? The universe is filled with other exotic homes. There are planets and binary star systems that have two suns in their sky, experiencing complex cycles of light and shadow that we can barely imagine. There are planets orbiting tiny, dim red dwarf stars, so close that they are tidally locked, with one side in perpetual daylight and the other in eternal night. A day on such a world would mean a journey around the planet. There are even planets found orbiting pulsars, the dead, spinning cores of massive stars. These worlds are bathed in lethal radiation, a truly hellish environment. Yet they exist, they persist. They are, in their own way, home to a particular set of physics and chemistry. PSO J318.5-22 represents the ultimate extension of this idea. It is a world whose home is the entire galaxy. It is not tethered to any single star. It is a citizen of the Milky Way, its path dictated by the collective gravity of 100 billion stars. Its journey is its home. This is a profound philosophical shift. It moves us away from a parochial, system-centric view to a more galactic perspective. It suggests that a planet does not need a star to have an identity. It does not need to be part of a family to be a complete and complex world. It just needs to be. Perhaps our definition of home has been too narrow. Perhaps home is not a place you are tethered to, but simply a place where you can exist. For PSO J318.5-22, that place is the great, dark, open road of the interstellar medium. It challenges us with a question. Is home a place of stability and connection, Or is it simply the space you happen to occupy on your journey? The potential existence of trillions of rogue planets adds a fascinating and perhaps chilling new layer to one of the most profound questions in science, the Fermi paradox. The paradox, named after physicist Enrico Fermi, is simple. The universe is vast and ancient. There are hundreds of billions of stars in our galaxy alone, many of them with planets. Statistically, it seems almost inevitable that life, and even intelligent life, should have arisen elsewhere. Some of these civilizations should be millions of years older than ours and should have developed the technology for interstellar travel or communication. So, the paradox is this. If the universe should be teeming with intelligent life, where is everybody? This is sometimes called the Great Silence. For decades, we have been listening for signals from other civilizations with radio telescopes, and we have heard nothing. We scan the skies for evidence of alien technology, and we have found nothing. The Fermi paradox offers many possible solutions. Perhaps intelligent life is incredibly rare. Perhaps civilizations inevitably destroy themselves before they can achieve interstellar travel. Perhaps they're deliberately hiding from us. Or perhaps we're simply not looking in the right place. Now, let's introduce rogue planets into this equation. If the most common worlds in the galaxy are these dark, wandering orphans, it presents a new, intriguing possibility. We've been focusing our search for life on planets around sun-like stars. We look for the biosignatures of life on worlds that are like our own. But what if the most common form of life in the universe is not on the surface of sunlit worlds, but in the subsurface oceans of rogue planets, powered by geothermal energy? Such life would be completely invisible to our current methods of detection. It would produce no signals for us to receive. Its world would have no atmosphere whose chemistry we could analyze for signs of biology. It would be a silent biosphere. This could be a solution to the Great Silence. The galaxy could be teeming with life, but this life is hidden away in the dark, in the warm interiors of trillions of wandering worlds. This subsurface ocean hypothesis is both exciting and deeply melancholic. It would mean we are not alone in the universe, but it would also mean that we are fundamentally isolated. We might share the galaxy with countless other living worlds, but we would never be able to communicate with them or even know for sure that they are there. They would be hidden from us, and we from them, by impenetrable shells of ice and rock. The existence of PSO J318.5-22 doesn't prove this, of course, but it makes the idea more plausible by showing us that the raw materials, the planets themselves, are incredibly abundant. It forces us to consider that the universe might not be empty, but simply quiet. The cosmic stage might be full of actors, but they are all performing in their own soundproof rooms, unaware of the others. Is it a comfort to think that life may be everywhere, even if we are destined to never meet? Or is it the most profound form of loneliness imaginable, to be in a crowded room where no one can speak to each other? Let us bring our journey back to where it started, to that single, faint, red point of light in a sea of astronomical data. PSO J318.5-22, a string of numbers and letters designating an object 82 light years away. It is easy to get lost in the abstraction of science, in the masses and temperatures and spectral types. But the legacy of this discovery is a deeply human one. It is a story about curiosity, about our relentless and innate desire to look up into the darkness and understand what is there. For thousands of years, we have mapped the stars and traced the paths of the planets. This discovery is a continuation of that same ancient impulse. The legacy of PSO J318.5-22 is that it fundamentally changed our mental picture of the galaxy. Before it, the idea of a rogue planet was a theoretical curiosity, a ghost story told by astrophysicists. After it, it became a reality. It is a real place that we can point our telescopes to. This single discovery opened the floodgates for a new field of astronomy, legitimizing the search for and study of these wandering worlds. It has inspired new theoretical models new observational strategies and has become a key target for our most advanced telescopes. It has proven that we have the technological capability to find these needles in the cosmic haystack. Its legacy is also one of perspective. It has shown us that planetary systems can be violent and that not all planets get to have a stable home. It has shown us that a planet can be a world unto itself, generating its own heat and weather without the influence of a star. It has served as a pristine laboratory, allowing us to understand the nature of planetary atmospheres in a way that was previously impossible. It has deepened the mystery of the Fermi paradox and broadened our conception of where life might be found. All of this from one faint dot of light. This is the power of a single crucial discovery. It acts as a catalyst, sparking new questions and opening up entirely new avenues of research. It reminds us that the universe is always more strange, more complex, and more wonderful than we can imagine. For every question we answer, a dozen new ones emerge. The discovery of PSO J318.5-22 did not provide us with a neat and tidy conclusion. Instead, it flung open a new door into a dark, unexplored room of the cosmos and invited us to step inside. The true legacy of this lonely planet is not in the answers it has given us, but in the profound and beautiful new questions it has taught us to ask. It stands as a testament to the idea that sometimes the most significant discoveries are the ones that remind us just how much we still have left to learn. Our journey to the edge of our understanding is coming to a close. We have traveled over 80 light years to meet a world of eternal twilight, a world without a sun, a world we call the loneliest planet in the universe. We have explored the chaos of its birth, the science of its discovery, and the profound questions its existence raises about life, home, and our place in the cosmos. We have learned that our galaxy is likely filled with trillions of these wandering worlds, a vast, unseen population that outnumbers the stars themselves. And now, we return. We return to our own island of light, our solar system. We return to a world defined by its relationship with a star. Here, we have sunrises and sunsets. We have the changing of the seasons. We have the comforting, predictable cycle of day and night. After visiting a place of such profound solitude and darkness, perhaps we can see our own world with new eyes. The light of our sun, which we so often take for granted, might seem a little brighter. The blue of our sky, a little more precious. The stability of our orbit, a little more miraculous. PSO J318.5-22 is a mirror. In its isolation, it reflects our connection. In its darkness, it reflects our light. In its eternal, solitary journey, it reflects the beauty of our own cosmic home. It teaches us that the universe is vast enough to contain every possibility, from the brightest, hottest stars to the coldest, darkest planets. And every single one of them, from our bustling Earth to that lonely wanderer, is a part of the same grand cosmic story. Thank you for joining me on this plunge into science. I hope this journey has been both enlightening and restful. As you drift off to sleep, perhaps you will dream of swirling iron clouds, of a sky with no sun, and of the silent, beautiful dance of the cosmos. Remember your favorite planet that you thought of at the beginning. Now you have a new one to consider, a world that reminds us that even in the most profound loneliness, there is a story of resilience, of beauty, and of wonder. Rest well.